Hello and welcome to this video. This is the third video on curve fitting. In previous videos, we have seen the derivation of least square method and how to fit given data in linear and quadratic equation. In this video, we will see how to fit given data in power and exponential equation. Fitting of power and exponential equation is based on linear curve fitting by using least square method. So, first we will solve an example based on least square method to fit a straight line. So, example is like this. Using least square method, fit a straight line to following set of data. So, here x values and respective y values are given. And we have to fit a straight line equation. So, this is the equation of straight line. Fitting of this given data in straight line equation means we have to find values of a0 and a1. To find values of a0 and a1, we have seen in derivation of least square method, we need to solve this matrix. So after solving this matrix, we will get the values of a0 and a1. So if we use Cramer's rule to solve this matrix, then we will get formulas for a0 and a1. So if we use Cramer's rule to solve this matrix, then we will get formula for a0 and a1. So let us see how to use Cramer's rule to solve such a matrix. So let us consider a general matrix for two equations to unknown. Now here we have to find out values of x and y. So if you use Cramer's rule to find values of x and y, then to calculate value of x, at numerator we have to take the determinant of matrix, in which we have to replace the first column of coefficient matrix by right hand side matrix. Means here we have to replace this a11 and a21 by b1 and b2 respectively, and we have to take its determinant at numerator, and at denominator we have to take the determinant of this coefficient matrix. So to calculate determinant, we have to take the cross product. So determinant of this matrix will be b1 into a22 minus a12 into b2, and determinant of denominator matrix is a11 into a22 minus a12 into a21. So by putting values of these constants, we will get value of x. And to find value of y, at numerator we have to take the determinant of matrix, in which we have to replace the second column of coefficient matrix by right hand side matrix. So here we have to replace a12 by b1 and a22 by b2. So at numerator we have to take its determinant, and at denominator we have to take determinant of coefficient matrix. So at numerator we will get a11 into b2 minus b1 into a21, and denominator will be same as x value. Now we will use this Cramer's rule to solve this matrix. So here we have to calculate the value of a0 and a1. Now if we use Cramer's rule, then to calculate value of a0, we have to replace this first column by this right hand side matrix. So if you replace this, then to calculate value of a0, at numerator we have to take its determinant. So let us replace this first column by right hand side matrix. So here we have to take its determinant at a numerator. Its determinant is summation of yi into summation of x square minus summation of xi into summation of xi yi. And at denominator we have to take the determinant of coefficient matrix. So this is the coefficient matrix. So its determinant will be n into summation of xi minus summation of xi into summation of xi. Now to calculate value of a1, we have to replace the second column of this coefficient matrix by right hand side matrix. So if we replace, then we will get formula for a1. Now here we will replace this column by right hand side matrix. So we will get this matrix. So its determinant will be at numerator. So determinant is n into summation of xi yi minus summation of xi into summation of yi, and denominator will be same as previous case. So in this way, if we solve this matrix by using Cramer's rule, then we will get formulas for a0 and a1. Now to solve this matrix, we need value of en, summation of xi, summation of xi, then summation of xi square, summation of yi, and summation of xi yi. So to calculate these constants, we will prepare a table. So first we will write given data in tabular form like this. So in first column it is serial number, then second column is X values, then these are the Y values. Now here we need X square values and XY values. So we will calculate X square values and XY values. X square values means square of each X values. For example, first X square value is square of 2, that is 4. Then square of 4, it is 16, and so on. Similarly, XY value means product of X into Y values. So for first XY value, it is 2 into 0.1825, which is equal to 0.365, and so on. So here we need the summations. So let us calculate the summations. So this n means number of data points. So here number of values are 5. So n is equal to 5. Then if we add all these X values, then we will get summation of X. Then if we add all these Y values, then we will get summation of Y. Then if we add all these X square values, then we will get summation of X square. Then if we add all these XY values, then we will get summation of XY. Now if we put all these values in this matrix, then we will get this matrix as like this. Now by using Cramer's rule, we will get these formulas, and by putting respective values, we will get A0 is equal to 0.05724 and A1 is equal to 0.04149. So here it is not compulsory to solve this matrix by using Cramer's rule. We can also use Gauss elimination method to solve this matrix. So if we put A0 and A1 in this equation, then we will get Y is equal to 0.05724 plus 0.04149x. So this is the straight line model for given data. Now we can cross check our solution. So this is given example, and this is the straight line model for given data. So in this model, if we put values of X, then we will get respective values of Y. So let us put X is equal to 2. So if we put X is equal to 2, then we will get Y is equal to 0.1402, which is slightly lower than this actual value. Then let us put X is equal to 4. So if you put X is equal to 4, then we will get Y is equal to 0.2232, which is slightly greater than this actual value. Then if you put X is equal to 6, then we will get Y is equal to 0.3061, which is slightly greater than this actual value. Then if you put X is equal to 8, then we will get Y is equal to 0.3892, which is nearly equal to actual value. Then if you put X is equal to 10, then we will get Y is equal to 0.4721, which is slightly lower than actual value. So here, by putting different X values, we will get respective Y values from this model equation. Now here, in given problem, number of data points are 5. So best fit for this given data is 4th order polynomial equation. Now we can check the goodness of this equation by calculating correlation coefficient. So let us calculate correlation coefficient. So this is the formula for calculating the correlation coefficient. Here ST is equal to summation of I going from 1 to n yi minus y bar bracket square. Here this yi means given values and y bar means mean value of y. Then SR means summation of I going from 1 to n ei raised to 2. Here ei is the respective error in measured value and modeled value. So we can check the goodness of our fit. For perfect fit, SR is equal to 0, means error is equal to 0. So if SR is equal to 0, then R will be equal to 1. So for R is equal to 1, we can say fit is perfect fit. For R is equal to 0, SR is equal to ST, and here fitting is not good. So in this way, value of correlation coefficient varies from 0 to 1. So let us calculate correlation coefficient for this given example. So these are the measured values, means values of y which are given in the problem, and this is the mean of measured value. And these values of y are calculated from linear model of given data. So to calculate correlation coefficient, we have to calculate the value of ST. So here if I is equal to 1, then here we have to take y1 minus y bar bracket square, means this 0.1825 minus this 0.30618 and it's a square, then plus 0.2019 minus 0.30618 bracket square and so on. So if you calculate this, then we will get ST is equal to 0.074945. Then to calculate the value of SR, we have to calculate error in each values of y. So if I is equal to 1, then we have to take measured value minus model value. So if I is equal to 1, then it is 0.1825 minus 0.1402 and it's a square, plus 0.2019 minus 0.2232 and it's a square, and so on. So if you calculate this, then we will get SR is equal to 0.006087. So if you put this ST and SR in this equation, then we will get correlation coefficient as 0.9585. So for perfect fit, value of R is 1. So that's why there is slightly variation in measured values and values calculated from the model equation. Now we will solve one example based on power fit. So let us consider the same data points, and here by using this table we have to fit a curve of the form y is equal to a into x raised to b. So here we can convert this power equation into linear equation by taking log on both sides. So if you take log on both sides, then we will get log to the base of y is equal to log to the base of a plus b into log to the base of x. So here power of logarithmic term will be the coefficient to this log term. So if you compare this equation with standard linear equation, capital Y is equal to a0 plus a1 capital X, then this a0 is equal to log to the base of a, then this plus sign as it is, then this a1 is equal to small b and capital X is equal to log to the base of x. So on comparing, we can write these relations. Now instead of given value of y, if we take log to the base of y, and instead of given values of x, if we take log to the base of x values, then we will fit the linear equation for given data. So to fit the linear equation, we have to solve this matrix. So after solving this matrix, we will get values of a0 and a1. But we need values of a and b to fit power equation. So by using these relations, we can calculate values of small a and b. Here we have a0 is equal to log to the base of a. So we can rewrite that equation as a is equal to e raised to a0. That is, if you take exponential on both sides, then we will get a is equal to e raised to a0. So here exponential of this term will be equal to a, and exponential of a0 is e raised to a0. And from this relation, value of a1 is nothing but value of b. So in this way, we have to convert this power equation into linear equation. Then we will get values of a0 and a1, and after that we will get values of a and b in power equation. So here to solve this matrix, we need to prepare a table. So first column is serial number, then these are given values of x, then these are the given values of y. But here we have to take x as log x and y as log y. So we will take log x values and log y values. So here log to the base of 2, it is 0.6931. Log to the base of 4 is 1.3863, and so on. For y values, if you take log to the base of 0.1825, it is equal to minus 1.7010, and so on for other values. Now here we need x square values and x into y values. So we will add these two columns. So number of data points are 5. Then here it is summation of x values. So here we have calculated summation of x values, then summation of y values, then summation of x square values, and summation of x into y values. So here if you put these values in this matrix, then we can solve this matrix by using Cramer's rule, or you can use the Gauss elimination method. So here I have solved this matrix by using Cramer's rule. So if we use Cramer's rule, we will get formulas for A0 and A1, and by putting respective values, we will get A0 is equal to minus 2.2840 and A1 is equal to 0.6202. Now we have A0 is equal to log to the base of A. So from this we can rewrite this equation as A is equal to e raised to A0. So if you put A0 is equal to minus 2.2840, then we will get value of A as 0.1018. And from this relation, value of A1 is nothing but value of B. So value of B is equal to 0.6202. So if you put these values of A and B in this power equation, then we will get y is equal to 0.1018 into x raised to 0.6202. So this is the power model for given data points. Now here we have taken log to the base A on both sides. So relation between A0 and A1 is A is equal to e raised to A0. So if you take log to the base 10 on both sides, then we will get relation as A is equal to 10 raised to A0. So when we take log to the base 10 on both sides, then here we need to take 10 raised to A0. So in that case also we will get the same solution. Now we will cross check our solution. So this is the given problem and this is the power fit for given data points. So let us put x is equal to 2. So if you put x is equal to 2, then we will get y is equal to 0.1564. If we put x is equal to 4, then we will get y is equal to 0.2405. If we put x is equal to 6, then we will get y is equal to 0.3092. If we put x is equal to 8, then we will get y is equal to 0.3696. And if we put x is equal to 10, then we will get y is equal to 0.4246. So these values are slightly different from these measured values. So here also we can calculate the correlation coefficient. So these are the measured values of y, that is given values of y, and this is the mean of measured values, and these are the values of y which are calculated from modeled power equation. So here we have to calculate value of correlation coefficient. For this, if you calculate value of ST similar to previous example, then we will get ST is equal to 0.074945, and if you calculate value of SR, that is summation of error square, then we will get SR is equal to 0.012087. So if we put these values of ST and SR in this equation, then we will get R is equal to 0.9158. So here also this correlation coefficient is slightly lower. So that's why there is difference between measured values and modeled values. Now let us solve one problem based on exponential curve fitting. So let us consider same data points, and by using this table we have to fit a curve of the form y is equal to a into e raised to bx. So here also by taking log on both sides, we can convert this equation into straight line equation. So here if we take log to the base on both sides, then we can write log to the base of y is equal to log to the base of a plus here log to the base of e is 1. So log to the base of e raised to bx, it is bx. So on comparing with linear equation of the form capital Y is equal to a0 plus a1 into capital X, then we can write capital Y is equal to log to the base of y, then a0 is equal to log to the base of a, then this a1 is equal to b, and capital X is equal to small x. So we will get these relations. So similar to previous example, to find values of a0 and a1, we need to solve this matrix. So after finding values of a0 and a1, we will get this straight line equation, and by using these relations, we can get values of a and b. So here we have a0 is equal to log to the base of a. So by taking exponential on both sides, we will get a is equal to e raised to a0, and here value of a1 is same as value of b. So to solve this matrix, we need to prepare a table. So here first column is serial number, then these are the values of x, then these are the given values of y. So here small x values we can take as capital X. So capital X values are same as given values of x, but instead of y values we have to take log to the base of y values. So we will calculate that column. So here log to the base of 0.1825 is equal to minus 1.7010 and so on. Now here we need x square values and xy values. So we will add these two columns. So let us calculate the summations. So here this n is number of data point, which is 5. Then this is summation of x, then summation of y, then summation of x square and summation of x into y. So by putting these values in this matrix, we will get this matrix, and we can solve this matrix by using Cramer's rule or by using any other numerical methods. So if you solve by using Cramer's rule, then we will get A0 is equal to minus 2.0622 and A1 is equal to 0.1338. Now we have relations between A0 and A1 and A1 and B. So from this relation we can write A is equal to e raised to A0. So if you put A0 is equal to 2.0622, then we will get A is equal to 0.1272 and value of A1 is nothing but value of B. So B is equal to 0.1338. So if you put these values of A and B in this exponential equation, then we will get y is equal to 0.1272 into e raised to 0.1338 into x. So this is the exponential model for given data points. So here we will cross check our solution. So this is the given data points and this is the exponential model of given data points. So here by putting different values of x, we will get respective values of y. So let us put x is equal to 2. So we will get y is equal to 0.1662, which is slightly lower than actual value. Then if you put x is equal to 4, then we will get y is equal to 0.2172, which is slightly greater than actual value. Then if you put x is equal to 6, then we will get y is equal to 0.2839, which is slightly greater than actual value. Then if you put x is equal to 8, then we will get y is equal to 0.3709, which is nearly equal to this actual value. And if you put x is equal to 10, then we will get y is equal to 0.4848, which is slightly lower than this actual value. So in this way, we will get values of y which are slightly different than actual value. Now here also, to check the goodness of this fit, we will calculate correlation coefficient. So to calculate correlation coefficient, these are the measured values or given values of y, and this is the mean of measured value. These are the y values which are calculated from exponential model of given data. So to calculate the value of correlation coefficient, we have to calculate the value of ST. So when I is equal to 1, we have to take 0.1825 minus 0.30618 and it's a square, and so on. So if you calculate the value of ST, then we will get 0.074945. Then to calculate the value of SR, we have to take the summation of square of error in y values. So when I is equal to 1, we have to take 0.1825 minus 0.1662 and it's a square, plus when I is equal to 2, we have to take 0.2019 minus 0.2172 and it's a square, and so on. So if you calculate SR, we will get 0.001733. So if you put this ST and SR in this equation, then we will get correlation coefficient as 0.9883, which is near to 1. So here if we compare correlation coefficient for linear, power and exponential fit, then correlation coefficient is more or near to 1 in case of exponential fit. So we can say for given data, exponential fit is better than linear and power fit. But this may not be true for all types of data. So depends upon nature of given data, best fit equation may be different. But for this given problem, best fit is exponential fit. Now there can be different form of power equation. So if we have to fit the power equation of the form y is equal to a into b raised x, then we can solve this type of example by using similar procedure. So we can take log on both sides. So if we take log on both sides, we will get this equation, and if we compare with standard linear equation, then we will get relations between capital Y and small y, a0 and a, then a1 and b, and capital X and small x. Then by solving this matrix, we will get a0 and a1, and to get values of small a and small b, we can use these relations, and here by using this relation we can take exponential on both sides, and we will get a is equal to e raised to a0 and b is equal to e raised to a1. Now instead of log to the base e, if you take log to the base 10 on both sides, then we will get log to the base 10 of y is equal to log to the base 10 of a plus x into log to the base 10 of b. So if you compare with standard linear equation, then we will get relations between these variables. So again we can solve by using linear fit, and we will get values of a0 and a1. So by using these relations, we can calculate values of small a and small b. So here from this relation, a0 is equal to log to the base 10 of a, we can write a is equal to 10 raised to a0. So 10 raised to this term is equal to a, and 10 raised to a0 is 10 raised to a0. Similarly, from this relation, we can write b is equal to 10 raised to a1. So in this way, we can fit any type of power equation by using this procedure. Thank you for watching.